Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay Raj, back with yet another geometry video for you all. Our new lesson topic of focus is all about radians and sectors. So we're going to be moving into a bit more of complexity with our circles, some items that you're not necessarily used to or experienced with in previous terms, especially throughout our geometry course. We're going to be going into different units of measures, such as radians, and different aspects of circles, which include sectors, as both of these items that we're going to be looking at today will correlate with one another very closely. So today we're going to be looking at what exactly sectors are and how they can be identified by a different unit. But before we jump into the meat of today's lesson, please make sure to smash that subscribe button down below, hit that like button on this video, as well as turning on post notifications by clicking that little bell icon right next to the subscribe button, so you don't miss out on any of our channel's latest uploads. All of those things are very greatly appreciated. So today we're going to be looking at in depth what sectors are in correlation with circles and how exactly they can be identified and measured through a different unit other than degrees. Hint, hint, we're going to be looking at radians today. I'm sure many of you have heard of radians before, but never really went in depth with it because it's more of a trigonometric function and also a circle function, a circle measurement as well. So it's a very complex measurement, and it is derived from the circle. So it's of utmost importance that we go over it and look at it today. So let's jump right into it. Let's look at radians versus angles. So I'm sure many of you have already been experienced and utilized angles, especially throughout this geometry course. If you followed me up to this video, angles are very common. They're in your customary and metric systems. It doesn't matter what part of the world you are, they are consistent in those systems. Although they're not stated as compound matter, they are utilized for general construction. So angles are very, very common, and they are the most dominant. A full rotation of your angle, 360 degrees, is representative of your circle. But now we're going to be looking at the circle to derive a different angle measure. Instead of utilizing the angle to derive the circle, we'll do the complete opposite and derive a new measure called radians. So let's look at radian correlation. Let's look at what radians have in common with circles and how we can actually utilize them apart from angles. Radians aren't actually as commonly used compared to angles in just about any real life situation, except for the matter of fact that they do have heavy correlation with circles, and that they can be often utilized with circles when it comes to specific formulas, such as our sector formula that I'm going to be showing you today. So length can be measured in different units with inches and centimeters. Likewise, angles can be measured in degrees and radians. All this is just a comparison between radians and angles, which are two different measurements. They're two different linear measurements, such as inches and centimeters. Either one can have their own benefits, but in this world and in this day and age, angles are much more superior, as I stated before. But there are conversion scales between degrees and radians that prove that they are on the same basis, and they can represent the same similar values that are accurate as well. So angular measurements are standalone units, meaning you can be given any real-life example or any two rays that develop an angle, and you can get that angle measure, which is in degrees. But then again, you have your radian, which is a different form of your given angle, and it's going to be in a different form of measurement. So the reason that I say radians versus angles is that angles are representative of degrees. However, radian angles are representative of your measurements called radians. That's why I've titled this slide as such. And so radians more heavily correlate with angles in circles, such as your central angles. But your degree measures, your regular angles, are going to be universally used. They're going to be universally utilized. So this is an example of what we've been referring to in previous videos. I've showed you what a segment is, your chord, your arcs on your circle. But now we're just going to be combining both of those to develop our sectors. And we're going to be utilizing sectors and radian measurements to actually develop our angle measurements, to develop the sector formula and calculate sector areas. So if we look here, this will be our central angle over here. And we can describe this in both degrees or radians. We want to focus more heavily on radians, and we're going to be also looking at conversion scales as well. And then, of course, these are your traditional angles, such as your straight angles, 0 degrees, 45 degrees, 90 degrees, 180 degrees, and 360 degrees. Radians do not have symbols such as degrees in your degree symbol. It's going to be a little heightened small 0 at the top, as shown here, as such. But radians do not have symbols. They're just going to be your plain numeric value. And of course, they have correlation with pi because they have to do with the circle. So let's move on. Let's look at radians and conversions, part 1. So let's look at exactly what radians are, and then let's look at converting them to degrees. And afterwards, we're going to utilize them and correlate them with our circle values and our sectors. So a radian is the measure of a central angle of a circle that intercepts an arc equal in length to the radius. So in turn, a radian is actually just a ratio that you're developing, and it's going to be a consistent ratio no matter what value you're given, because it's all going to revolve around your given circle. So what it's basically saying here in this definition is if you're given a given circle and you have two radii that intersect the side of a circle and form a sector, or if you just have an arc on a circle, which is just a boundary on a circle, all it's saying is it's the ratio between that arc length and the given radius, meaning if the radius is equivalent in length to the arc, that means it's going to be equal to 1 radian. That's exactly how it works, and it's going to be building up off of that. And the maximum amount of radians in a circle are 6.28 radians. So abbreviations for our two units of measures that we're going to be focusing on today are DEG, D-E-G for degrees, and RAD for radians, R-A-D. So if we look here at this example, we have this sector formed here by two radii, basically intersecting the outside of this circle here. And as they do, you're forming your arc. And the arc is going to be equivalent to R, which is your radius. So that's when your arc is equivalent to your radius length. We know that arcs are continuous measurements. Therefore, they can be given linear correspondence, such as length. And in this example, our radius is going to be equivalent and congruent to our arc. Therefore, it's going to be equivalent to 1 radian. So 1 rad. That's the equivalence right there, ratio. That's 1 rad. And also what I do want to highlight here is that, your central angle here, you're going to have opposite exterior arcs and other interior arcs. And as that intersection happens, it's your central angle that's actually being identified as 1 radian as shown here. That's the central identification. So let's move on. Radians and conversions part 2. Let's look at representation during calculation. So the central angle, which is theta, represented in radians, is the ratio of the arc length S to the radius R. So basically, like I showed you before, it's going to be a consistent ratio. It's when you're looking at your given arc length, which is a consistent unit, and you're comparing it to your radius. And if it's a 1-to-1 ratio, that's going to be 1 radian of length or of representation. And theta equals arc length over radius. Theta, we know that theta is our central angle, and it looks just like this. I've referred to this multiple times in my previous video, but here's a little cap right there. It looks just like that. That's theta. And theta equals arc length over radius, which is equivalent to S over R. So that's how you're going to calculate your central angle, which is going to be representative of your radian. So if we're looking over here, we can see that our arc length, which is S, is equivalent to our radius times our theta, or our central angle. Or we can just say here simply that theta is equivalent to our arc length over our radius. And that's always going to be true. It's always going to be your S over R. Therefore, if you have a smaller arc length than your radius, you can assume that it's going to be a decimal. And of course, if your S is greater than R, or your arc length is greater than your radius, it's going to be larger. That's why the entirety of the circle, if you have an arc that encompasses the entire circumference of a circle, that's going to be equivalent to 6.28, which is the total length of your given circle. So I'll write this out here. Total circumference equals 6.28 radians, or rads. So now we know that 6.28 radians represents the entire circumference. That means our central angle is worth 6.28 radians. Now, if we compare this to degrees, we know that the entire measure of a circle is equivalent to 360 degrees. So that's AKA, or also known as 360 degrees. And this is going to be always true under our conversion scales. So let's move on. Let's look at radians and conversions part 3, and let's look at our conversion scales. So if you look at this picture that I have here, it's just a layout of exactly what scale it is and what you're multiplying, your multiplication factor. So if you're given an amount in radians, what you're going to do is you're going to if you're given an amount in degrees and you want to discover what your radians are, so it's moving from degrees to radians, what you're going to do is you're going to multiply your degrees by pi over 180 degrees. And in this case, what's going to happen, it's actually just going to get smaller, because we know that our radians, they only go from about 1 to 7 when looking on a circle. So we can automatically tell that the amount of radians is most likely going to be much less than the amount of degrees. So therefore, you're decreasing in your numeric value. But now if we're trying to move from radians to degrees, this way to that way, moving from right to left, when we're trying to move from radians to degrees, we're actually going to increase that number. So we're going to multiply it by 180 and divide it by pi, given the amount of radians. So say, for example, if you had radians 6, sorry about that. If you had degrees, let's say 180 degrees, and if we had radians 4 radians, how would we convert those? So if we look here at this example here, we have 180 degrees times pi over 180. So we would do 180 degrees over 180 degrees times pi. So it's 180 degrees pi over 180, which simply equals pi in this case because it's a semicircle. So they cancel out. And then for this example, so I'll draw the line there. And then for this example here, we have radians times 180 degrees divided by pi. So we're going to do 4 times 180, which equals 720. And then 720 over pi is our representation for the number of degrees for this equation given here. All right, let's move on. Now let's look at areas of sectors. So we're going to be applying our radians and, of course, our degrees to exemplify these. And we're going to try and calculate areas of sectors, also discovering exactly what they are. So this is part 1. So let's look at origins of sectors. A circle's central angle is measured in radians or degrees, and the area of a circle's formula is adjusted based off of which unit of measure is being used. So that basically goes without saying, if you're going to utilize degrees to calculate your given sector or your given arc, it's also going to be representative of a continuous length. Although your length is going to be the same, the whole process that you're utilizing is going to be different because you're utilizing 2 different measurements. But thankfully, we have our conversion scales, and it doesn't matter which matter that we're going. We just need to know what the answer is requiring us to calculate and represent for and be representative of. So the traditional area of a circle is pi r squared. We know that. Pi is always going to be consistent. I just want to say that. So pi is always consistent. And that's very important to know. It's a universal term. So if we look here, we have our major sector and our minor sector here. So our major sector is what's given, what's being focused on here in this example, and then our minor sector is shown here. Whenever you're given a sector is merely formed, as I showed you in my previous video. It's formed when you have 2 chords shown as by these white lines. They're intersecting the circle and they're intersecting at the center, so they're originating from the center, and these 2 segments are going, or these 2 radii are going and intersecting 2 points on the circle. Once you've developed that, you're creating 2 different sectors. One sector, which could be your sector of focus, such as this larger sector, this major sector here. But once you're doing that, you're also forming the inverse of that sector, which in this case, since it's a major sector of focus, the sector that's being formed, you're going to have a minor sector. And just keep in mind, a major sector is a sector that is larger than 180 degrees, or a semicircle, and a minor sector is less than 180 degrees, less than a semicircle. And that's drastically shown here, just to emphasize on that. And yes, we will be utilizing our given central angles. And what we're basically going to do, as I will explain in the next slide, we're going to utilize our central angles. We're going to keep that ratio consistent and utilize our circumference in order to develop our areas of our given sectors. So now moving on to our next slide, areas of sectors part 2. We're going to be looking at the main properties that are going to define what sectors are. So this is going to be all about sectors. We're going to look at the basic definition, and we're going to correlate that to what we're here for, to calculate the areas of our sectors and putting them in forms of degrees and both radians as well. So if we're looking at a sector, it's in a circle. It's a region with boundaries of 2 radii, and it is part of a circle. So if you're thinking about a pie piece, and say, for example, you have a central point of your circle, all you're doing is cutting out slices of your pie, and they're going to be triangular chunks. That's exactly what your sectors are. So once you cut out your triangular chunk, whatever's left outside is going to be the remaining given sector. It's going to be your remaining sector outside. But the sector of focus will always be in a triangular manner. Unless, of course, it's larger than a semicircle, in which it would be a major arc that defines it. So sectors are congruent when 90-degree central angles are developed, and I'm going to show you what that looks like. So keep in mind we have 360 degrees in our given circle. So 360 degrees, as shown here. And when we're given a circle, we can divide those 360 degrees in order to develop different segments, such as quadrants on a coordinate plane. You're dividing that plane up into 4 different quadrants that have their own different properties. In this case, we're dividing that 360 degrees that defines the circle, and we're going to limit it into concentrated rotations. Those rotations are going to be of 90 degrees. So if we're looking at this central angle here, located in the center of the circle, as such, it's going to be of 360 degrees. And looking at those 360 degrees, we can tell that this is being divided into 4 different quadrants as such. And those quadrants are going to be your formal sectors. And when you're doing so, each and every separate sector is going to be equivalent to 90 degrees, as shown. 90 degrees. Splitting that whole of 360 degrees into 4 equivalent parts. This is the only time when all sectors are going to be equivalent when given 2 different chords. So it's going to be 4 90-degree angles, and that's when you divide 360 degrees. Equals 4. And that's exactly what we're going to be doing. We're going to try and utilize formulas in order to calculate the areas of our said sectors. Now looking at areas of sectors part 3, let's look at the areas of sectors. So let's look at their formal formulas in the next slide, but I just want to explain how exactly these formulas are brought about. So sectors are bounded by 2 circle radii, and those central angles can be converted from degrees to radians and vice versa. So those are the defining factors. That central angle is what's actually going to develop the whole area of your circle. You need absolutely nothing else once you're given that radius and that central angle. So just to recap what I had previously shown you, if we're given radians equals, we're trying to discover our central angle. For our radians, it's going to be angle times our given pi over 180. So pi over 180, and then for degrees, it is going to be our angle times our 180 over pi. Smaller to larger when you're going from radians to degrees, and larger to smaller when you're going from degrees to radians for the numeric values. So let's move on. Areas of sectors, part 4. Let's look at the calculation of sectors. So a formula of a sector in degrees is your theta, or your central angle, over 360 degrees, multiplied by the given area of your circle, so pi r squared. Now, in essence, all you're doing here is you're giving your fraction of your circle. So we know that sectors are going to be some sort of consistent fraction of your given circle, and this is going to be in form of degrees. So once you're given your circle, you know that it's 360 degrees in angles, and we're given a central angle here. So we're going to divide our theta, or central angle, by our 360 degree angle, and we're going to develop our fraction and just multiply that to the given area of your circle, which is pi r squared. And you're already given your radius since you're able to develop a central angle. And then the formula of a sector in radians is going to be your theta, your central angle, over 2 times your r squared. Multiply by your r squared. And keep in mind, this is in form of your radians. This is going to be your central angle in radians over 2 times r squared. Very straightforward. So if you have an 80-degree angle here, 80 degrees here, and we're trying to plug this in for our degrees, the formula of a sector in degrees, we're going to do 80 over 360. And that's going to be simplified. We can divide each one by 40, so we get 20 over 90, in which we can divide each one by another 10, and we can get 2 over 9. So in essence, it's going to be 2 over 9 times pi with our given radius, which is x squared. Now, if we're looking at our radians here, for example, or pi over 2, and we're given this in radians, what we want to first do is, convert our 80 degrees into radians. So we know that in order to do that, we're going to be moving from larger to smaller. So we want to divide by a larger amount. So it's going to be 80 degrees times pi over 180. And that's going to equal 80 pi over 180, which then simplifies. We can divide each value by a given 10 and then a 2, so that's going to be another 20. So it's going to be 4 over 9 here in this case. It's going to be 4 over 9. And with that given ratio, we can multiply, we can tell that it's 4/9 radians, so it's going to be 4 over 9 divided by 2 multiplied by our r squared. All right, everyone, so that'll be it for today's video. I hope you all enjoyed. This has been the eCoreAcademy e-learning platform today. Please make sure to like and subscribe down below and turn on post notifications so you don't miss out on any of our latest uploads. Also, visit our website at www.ecoreacademy.org to see full unlocked access to what we as an online e-learning platform actually offer for you. We have integrated note sheets, quizzes, and worksheets that go along with each and every single one of our videos under their own lessons and their own course studies and subject categories. So please go head down there, make an account for free, and get full unlocked access. Also, feel free to email us at ecoreacademy@gmail.com if you have any questions or if you just want to reach out to us. And finally, visit our socials down below at Facebook, Twitter, and Instagram. See what kind of content we have there and use those mediums to share all of our videos. Once again, everyone, that'll be it for today's video. I hope you guys enjoyed. This has been AJ, and I will see you guys in the next one. Peace.